Starting with this video, we'll discuss feature engineering. Feature engineering is a collection of methods used to create new features based on the existing features in a dataset. To perform feature engineering effectively, it's essential to have a thorough understanding of the existing dataset. Sometimes, new features can be created using simple mathematical calculations, while in other cases, creating meaningful features may require human knowledge and domain expertise. First, let's look at the formal definition of feature engineering. Feature engineering is a data processing technique that involves extracting, transforming, or optimizing features from raw data to create more useful features for training models. As we mentioned earlier, the goal of feature engineering is to create new features that benefit the learning task, allowing us to build a better performing model more efficiently. We can broadly divide feature engineering into four categories: feature selection, feature extraction, feature transformation, and feature combination. Feature selection involves manually examining the raw dataset and discarding features that are completely irrelevant or unimportant. This process often requires human knowledge. If we include irrelevant features in a machine learning task, the model will still attempt to find relationships between them and the target, wasting a significant amount of time on meaningless patterns. By eliminating such features, we can make the learning process more efficient and focused. In this example, we aim to train a model using these features to predict house prices. Clearly, the more information we have about the houses, the easier it will be for the machine to uncover the underlying patterns in the data. As a result, when new information about a house becomes available, the model will be able to make more accurate predictions. However, in this dataset, we have a feature representing stock prices. While stock prices might influence the real estate market in certain situations, in this dataset, we have no context for what these numbers represent. If we include this feature in the training process, the machine will waste significant resources trying to find meaningless patterns. Therefore, in this example, we should remove the stock price feature entirely to avoid unnecessary computation and noise in the model. Feature extraction involves identifying and extracting meaningful features from raw data, making their significance more direct and clear. At this step, it's important to slow down and carefully think through the problem. Our trained minds often overlook certain intuitions, but it's these very intuitions that can help the machine learn more effectively. By focusing on extracting features that capture essential patterns, we can improve the model's ability to understand the data. Now, let's continue examining this dataset. Take a moment to think about this question. When looking at the year-built feature, what is your intuition? I'm guessing you thought about how the year-built feature could help us determine whether a house is new or old. But have you ever considered why knowing the construction year immediately leads us to classify a house as new or old? This intuition is based on using the current year as a reference point. Without knowing the current year, it would be difficult to determine whether a house is new or old. For example, if we assume the current year is 2005, the newest house in this dataset would have been built in 1995, as a house from 2010 wouldn't exist in this context. So, the assumption behind determining whether a house is newer or older is to calculate the difference between the year-built feature and the current year. The larger the difference, the older the house is likely to be. So, how can we quantify this intuition to provide the machine with more straightforward data? The most straightforward way is to do what we just mentioned, to find the current year or select a specific baseline year based on the machine learning task. Then, calculate the difference between the construction year of each house and this baseline year. Clearly, the larger the difference, the older the house. Compared to using just the construction year as is, this difference provides a stronger and more meaningful pattern, making it easier for the machine to identify relationships and trends in the data. Specifically, finding new features doesn't mean we should immediately remove the old ones. This is especially true when the dataset size is relatively small. In such cases, we should make use of all available features, meaning we should retain year-built alongside the new features for the machine learning task. Feature transformation is another important category in feature engineering. In feature transformation, we mainly use mathematical and statistical methods to transform features that are not easy to work with into more usable forms. Let's continue examining this example. This time, let's focus on the house area feature. When you look at these three data points, what stands out to you? You might notice that the differences between the values in this set are quite large. If you recall what we learned earlier about data normalization, you'll realize that when the differences within a feature are significant, there's a high chance of outliers. On the other hand, if the numerical values across different features vary greatly, the model might unintentionally give less importance to some features. In either case, we should avoid having skewed data in the dataset. You might already be thinking that data normalization is a classic solution to address this issue. However, since we're discussing data transformation here, we'll explore some mathematical methods to reduce the differences in numerical values within a feature. The most common method is to apply a logarithmic transformation. As shown in this image, when we take the logarithm of a function with large variations, the resulting values of the logarithmic function are compressed into a much smaller range. This helps to reduce the scale of differences while preserving the relative relationships between data points. However, logarithmic transformations come with significant limitations. First, when numerical values are small decimals, the results of the logarithmic function can increase infinitely in the negative direction. Second, the input for a logarithmic function must be positive values, meaning it cannot directly handle negative numbers. These constraints limit its applicability in some datasets. Although logarithmic functions have some limitations, they are still one of the most commonly used mathematical transformations in practice. In our example, the house area feature doesn't contain negative values or very small decimals, making it an ideal candidate for applying a logarithmic transformation. This ensures the transformation is both effective and practical in this case. We can see that after applying the logarithmic transformation to the house area feature, the originally skewed data has been successfully compressed into a much narrower range. By using a logarithmic transformation, we significantly reduce the impact of the raw numerical values while preserving the relationships between the data points. Just like data normalization, if we care more about the relationships between data points rather than the raw numerical values, compressing the value range is one of the best practices. However, if the task requires us to retain the actual numerical values, such as predicting people's heights in a specific region, we should use the raw height data to train the machine. Let's continue examining this dataset. Do you notice any other inconvenient features? For example, are there any types of data that might be difficult for a machine to handle? You've probably realized that if we directly feed this dataset to a standard machine learning model, it won't understand the meaning of terms like city, suburb, or rural. Of course, we now have powerful generative AI models, like ChatGPT, that can handle such data. But these are pre-trained models. If we're training a model from scratch, it wouldn't recognize categorical data like this. In such cases, as we discussed earlier when learning about data transformation, we need to encode the dataset, that is, convert categorical values into numerical ones. This step ensures the data becomes machine-readable for training purposes. The best solution for this issue is likely the one-hot encoding scheme, as there aren't too many unique values in this categorical feature. We've already covered the details, advantages, and disadvantages of one-hot encoding in previous discussions. If you've forgotten, feel free to review that material. Remember, if a categorical feature has too many categories, one-hot encoding is not recommended, as it can cause the dataset size to grow exponentially, making it difficult to manage and process. Finally, let's take a look at the last category in feature engineering, feature combination. In feature combination, we create new features by combining existing ones. However, this process requires domain knowledge to ensure that the combinations are meaningful, rather than arbitrarily merging features without a clear purpose. Let's stick with this example and consider the following question. Based on this dataset, can we derive any more common or intuitive features that might influence house prices? Here's a screenshot from a popular real estate website. As you can see, when a realtor posts a house on the market, they highlight certain features in the most prominent position. In our current dataset, we already have information like the year the house was built and its age. Do you think we could derive any other useful information from these existing features? You might have thought of a feature like the average size of each room, or square feet per room. This is an important factor for buyers when considering a house, By explicitly providing this feature to the learning task, it could help the model learn useful patterns more quickly and improve its overall performance. This is a great example of the importance of feature combination. By simply dividing the value in the house area feature by the number of rooms, we can quickly create a new feature, square feet per room. This process of deriving a meaningful new feature from existing ones is what we call feature combination. Finally, let's quickly go over the advantages and disadvantages of feature engineering. This type of question is more open-ended, so there isn't a strict standard answer. As long as you understand the logic behind each category of feature engineering, you can freely respond to questions about its pros and cons. First, let's briefly discuss the advantages. Feature engineering allows us to create more features, giving us more options. By selecting the most relevant features, we can train a better performing model in less time. Additionally, if the features are more intuitive and rational, it becomes easier to interpret the model's predictions. As for the disadvantages, creating new features naturally requires more time, making feature engineering a time-consuming process. It also requires domain knowledge to understand how to handle the dataset properly, such as when combining features. Lastly, creating too many new features can introduce additional noise and increase the dataset's dimensionality, which in turn adds complexity. This could lead to overfitting, which is something we want to avoid. Therefore, one key principle of feature engineering is to extract and transform features that improve model performance while eliminating redundant or irrelevant features. In simple terms, if the raw dataset has too few features relevant to the learning task, use feature engineering to create more meaningful features. On the other hand, if there are already too many features, carefully perform feature selection to reduce noise in the dataset and improve the model's efficiency.